Here we're going to discuss more irreducible representations. We said that symmetry of some objects like a molecule or a line or a point or a coordinate system can be represented in many different ways mathematically, and we chose matrices to represent the symmetry. And we said that we can boil off all the extraneous information about these matrices and just be left with the essence of the symmetry and representation, and that's called an irreducible representation. These symmetries are summarized in what's called character tables. Let's take a look here. Here's a Wikipedia article on character tables. Make this a little bigger here. And let's take a look at, or actually the Wikipedia article, the tables of character tables. Okay, so here's a bunch of character tables for various symmetries. Remember, we had nomenclature depending on whether you had a certain number of various reflection planes, or rotation, inversion, and so on. And we had a flowchart in order to determine symmetry. All right, so here, there we go. Here's the C2V point group, and here's the character table for it. It's these numbers right here. Okay, we'll talk about these numbers here in just a minute, but there it is. That's the essence of C2V symmetry. They're irreducible representations like this, and anything you talk about that in the C2V symmetry has to be represented by one of these irreducible representations. Now remember what we said before. We went through the rotation and so on, and we said that the x transformed as 1 minus 1, 1 minus 1. Well, these character tables have in it on these extraneous or extra columns here. These are not part of the character table, but for instance, z transforms as 1, 1, 1, 1. Or has the irreducible representation as 1, 1, 1, 1, and y has this. So if we already knew about the character table, we wouldn't have to go ahead and do all those rotations and reflections and so on. We just look up in the character table. Now here, each one of the irreducible representations, which is a row going across here, that's how we represent, like z is represented in C2V symmetry as ones going across here. So no matter what operation you do, you always get the same thing. If the C2 does not change sign, if it remains 1, then the irreducible representation, these rows, is called A. Here it changes sign, C2 rotation, and this irreducible representation changes sign to -1, -1, so they're called B. And then the subscript 1 and 2 correspond to what happens when you do a sigma V. Okay, sigma V, if it's +1, subscript 1. If it's -1, subscript 2. +1, subscript 1, -1, subscript 2. So that's the nomenclature for this. So again, what you have labeling the columns are the symmetry operations, and labeling the rows are these particular irreducible representations. This would be the A1 representation. The A1, all symmetry groups have an A1 representation corresponding to all ones here. So that's the C2V and the character table for C2V. Let's take the look at the simplest one. That's C1. Here it is. C1 has just one element in it. That's called the identity matrix. All molecules have the identity matrix, and therefore even ones that have no further symmetry still have the identity matrix, and there it is, 1. So the identity matrix is totally symmetric. A is just 1. All right, so that's what a character table is. Now, this is interesting. The irreducible representations are orthonormal. Oh, what does that mean? Well, let's go down and take a look at the C2V. Here it is. We want to show that each irreducible representation, or this collection of irreducible representations, these collection of rows of numbers, are orthogonal. All right, so let's just figure out what we mean by orthogonal again. We have to define what we mean by this analogous what's called an inner product. So for example, when we had the two-dimensional coordinate system, x, y, we defined unit vectors along here, the I unit vector and the j unit vector, and that any vector in here, any point in this Cartesian coordinate system can be expressed as a linear combination of these orthonormal vectors. So what did we mean by orthonormal when we talked about these vector combinations? Well, what we meant was that, for instance, I times I, we want that to be equal to 1, and we're defining I times I as the length of I times the length of I times the cosine of the angle between them, and these are unit vectors, so this is equal to 1. And if we define the dot product as this, then I dotted into j, so we're sort of multiplying or doing the inner product. That's equal to 0 because the length of I times the length of j, well, that's 1 times 1, but the cosine of the angle between them, this is 90 degrees. Cosine of 90 is 0, so this is equal to 0. So these form an orthonormal basis set for the two-dimensional Cartesian plane. Then when we talked about orthonormal basis sets for quantum mechanics and wave functions, we defined the inner product as psi I star psi j, and we integrated this over all space. And if that is equal to 0, then psi I and psi j are orthogonal. And if it's equal to 1, that implies that, for I not equal to j, for I equal j, so in other words, you're squaring the wave function and integrating over all space, that implies that psi I is normalized. Okay, a fancy way to write this is say that this term is delta ij. So when I equal j, this term is 1. When I not equal j, this term is 0. This is called the Kronecker, K-R-O-N-E-C-K-E-R, I think that's how you spell it, Kronecker delta. All right, so here we've had orthonormal basis set. We talk about vectors, and we talk about what we mean by the dot product or the inner product. Here we have the orthonormal basis set of wave functions, and here we've defined what we mean by the inner product. Now what we have are irreducible representations. So these, we have to define what we mean by the inner product, and what we're going to show is that we just, for example, take A1 times A1, we'll get 1, or if we take A1 times A2, we'll get 0. So let's use the general symbol, that's what most people do, of gamma. So this is an irreducible representation. Okay, and we'll say gamma I times gamma j. That will be the 1 over h. This is the number of symmetry operations of the sum over I equal 1 to n of that particular value of the, I guess I'm using I and j, so let me use a k here, so not be confusing, times gamma j of k. What do we mean by that? And I maybe haven't written that quite right, but for example, let's do A1 times A1, okay? So A1 times A1. How many symmetry operations are there? There's 1, 2, 3, 4 symmetry operations. So this is 1/4. This is for A1 times A1, and you usually give this X with a cross around it, or plus with a cross around it, or a circle around it. That's 1/4. So what we do is take this 1 times 1, 1 times 1. So let me just rewrite it this way. A1 is 1, 1, 1, 1. And we're going to multiply that by 1, 1, 1, 1. And then we're going to add these things up. So let's actually do that. 1 times 1 is 1, plus 1 times 1 is 1, plus 1 times 1 is 1, plus 1 times 1 is 1. So this comes out to be 4. So that is equal to 1. So you see that A1 times A1, that irreducible representation A1 times irreducible representation A1, multiplied by itself, or we're defining the multiplication as this kind of multiplication here, that is equal to 1. Let's pick, say, A2 times B, we'll do it this way, times B1. What's that equal to? 1/4, total number of symmetry operations. Now let's see what A2 is. 1, 1, minus 1, minus 1. And B, what do we say? B1? B1 is 1 minus 1, 1 minus 1. 1 minus 1. All right, so let's multiply these and add them. 1 minus 1 minus 1 plus 1, that's equal to 0. So look at that, 0. When you multiply these two together, where we're defining this is the multiplication, we get 0. And what you'll find is that A2 times A2 is 1, same way B1 and B2, and then any two irreducible representations that are not the same is equal to 0. So that's kind of cool, and this will become useful later on. We'll see. But the irreducible representations are orthonormal. All right. Now, representations can be expressed as linear combinations of irreducible representations. Now, just like we did before, for example, when we express some wave function as some linear combination of some basis set wave function psi I, where this is the basis set, or any vector r as a linear combination, let's use a 2D Cartesian coordinate with C1 times I plus C2 times J. All right, so that's, so too can we express any representation as a linear sum of irreducible representations. So those are irreducible representations. I and J are a basis set. So the irreducible representations can be considered a basis set. And we can represent any representation as a linear combination of these irreducible basis sets, just like we did for these two cases before. And this basis set, we just said if we define the multiplication like we did in the previous slide, this basis set is orthonormal. And so are these if you make sure, well, you can make these orthonormal. Okay, so that's what that means. And then because of that, you can pick out, if you're given a reducible representation, you can reduce that to a linear combination of irreducible representations for reasons we'll just show now. So for example, here is this reducible representation. We know that because this is for C2V. Go over here and look up in the character table. Oh, C2V does not have this as a irreducible representation. So can we make this into a linear combination of irreducible representations? And the answer is yes, we can. Again, it all revolves around the fact that we have an orthonormal basis set. Now let's just do the example for in the 2D plane. So suppose we have R is, say, 3 times the I vector, so this is, I guess we're doing that, plus 4 times the J vector. So that's a vector which starts at the origin and goes up to this point, which is 3 on the x and 4 on the y, and we got that by going 1, 2, 3 on the x in the I direction and 1, 2, 3, 4 on the j direction. All right, we want to know how much I is in R. All right, what we do then is just take the dot product of I dot R. Because if we do that, that's I dotted into 3I plus I dotted into 4J, and that's equal to 3 times I dotted into I, I'm ignoring all the hats there, plus 4 times I dotted into J. Since I and J are orthogonal, this term is equal to 0. I shouldn't write that, so this term is equal to 0. This term, since they're normalized, that's equal to 1, so this just comes out to be 3. So to figure out how much I is in this total vector, you multiply by that particular orthonormal basis function there. So I will project out of this the number 3. Well, the same way with reducible representations. So for example, if you have a reducible representation, I guess if this is and if you now have an irreducible representation, so if this is an irrep, I guess we can call this a rep, a reducible representation, red rep, reducible red rep. That's kind of funny. Anyway, what this will do will be to project out how much gamma I, that's a particular irreducible representation, is in the reducible representation gamma. All right, so let's do that for that example. We have 4202. Okay, so what we want is 4202. All right, so that is our irreducible, our reducible representation. Now let's see, it's again, we want C2V symmetry. So let's go here, let's look at the A1. Let's project out of that how much A1 is in there. Okay, so A1 will take the irreducible representation corresponding to A1 and we'll multiply that by the reducible representation. And then of course we'll take, we'll have to normalize it, so it's 1/4 the number of symmetry operations in the group. So for the C2V, that's equal to 1/4. And I should put 1 over H here, where H is the number of symmetry operations, to be absolutely precise. So 1/4 times that, so that's equal to 1/4 times, let's see, A1, well that was the A1 is totally symmetric, so that's all ones. And this is 4202. And so when we multiply this through, that's 4 plus 2 plus 0 plus 2, and that's equal to 8, and we divide that by 4, that's equal to 2. So within this reducible representation, there are two A1s. Let's look at A2. We'll do this again, 1/4, the normalization there, A2, the gamma for A2, times, and I guess I should be consistent with what the textbooks use. This would be this funny symbol here, an X or a plus. I think it's an X, gamma. That's equal to 1/4. All right, A2 is all 1, 1, minus 1, minus 1. 1, 1. And this, the reducible representation is 0, 2, 0, 2. So we multiply this together. This is 4 plus 2 minus 0 minus 2. So that is 4. Divide that by 4, you get 1. So there's one A2 in that. And then now let's project out the other two. We'll go B1, projection of that, that'll be 1/4 of the irreducible representation by B1 times the reducible representation. B1, well, let's just see what B1 is. 1 minus 1, 1 minus 1. And we're going to do a 4202. That's reducible representation. That's 4 minus 2, 0 minus 2. Oh, that's equal to 0. So there is no B1 irreducible representation in this reducible representation here. Let's do B2. That'll be 1/4. The irreducible representation for B2 times the reducible representation. That'd be 1/4. B2. 1 minus 1 minus 1, 1. And we're doing 4202. So that's 4 minus 2 plus 0 plus 2. And so that is equal to 1. So there's one B2 in there. Okay, so we've extracted out each one of those from that total, how much each irreducible representation contributed to that total. So if we put all that together, we would say that the reducible representation gamma is composed of 2A1, 1A2, no of the B1, and 1 of the B2. So 2 of the A1 plus 1 of the A2, none of the B1, and 1 of the B2. So in this reducible representation, there's 2A1, 1A2, and 1B2. Now, let me do one more clarification here. This is the total number of symmetry operations in a group. All right. So let's take a look at, we did C2V. Let's look at C3V. Here's C3V right here. All right, so contrast and compare. C3V, you may remember, let's see if we can pull up that a nice website again. Here's the ammonia molecule, and we remember the ammonia molecule, actually it says right here, but we can figure that out. That's C3V symmetry. C3V symmetry has a C3 axis, and it has 3 planes. Okay, and it also has the identity element, of course. Let's look at the C3 axis. Here's the C3 axis, okay? So we can then maybe just see, and now we'll put the C3 axis coming towards you. If we rotate this by 360 degrees divided by 3, that's 120 degrees, we'll get the same molecule back. Actually, let's do that. Here comes the rotation. Yeah, that's counterclockwise rotation. There it is. Okay, so that's a C3 axis. But note that we can do one C3 rotation and then another one before we get back to the, quote, original structure. So if we label these, this is the first hydrogen. The first rotation takes the first hydrogen here. The second takes it there. And only to the third you get it back. So these C3 rotations are actually 2 of them. One is you rotate through 120 degrees, and the other is you start here and rotate through 240 degrees. Of course, if you rotate through 360 degrees, then that's the same as the identity operator. All right, so 120, or there's a 240. So there are 2 C3 axes. And then let's look at these planes here. Here's the sigma V planes. You see that there's 1, 2, 3 sigma V planes, and they all contain the C3 axis there. All right, so there are 3 sigma V planes. So the total number of symmetry operations here is 6. 1, 2, 3 planes, 2 axes, one where you rotate 120, 240, and then the identity element. So the total number of symmetry operations here is 6. However, group theory tells you that you can divide, sometimes you can collect symmetry operations into classes. Now what I want to convince you of is that by rotating around the C3 axis, you can convert one symmetry plane into another. Well, that sort of makes sense if we look at it this way. Take this symmetry plane. By rotating around the C3 axis, we can put that into there, and that into there, and that into there. So symmetry elements, in particular planes, that you can go from one plane to another, these 3 different planes, you can go from one to another by an operation of another symmetry operation, for instance, the operation of the C3. That means that all of these can be grouped into a class. Well, this means that all of these have the same character in the character table. So you could do, write out the character table and have 6 elements in there. In other words, 6 columns in your character table. But it turns out for all these that are in the same class, you have the same character. So you compress the character table by grouping these all together. And the same way with these C3 axes. So you see, well, the C3 axes, they're coincident, they're parallel, so any reflection in any one of these planes will convert the C3 axis that goes 120 into the C3 axis that goes 240. So any axes that are superimposed one on top of another are in the same class. So really, if you look at classes, there are only 3 classes. There's the identity, there's these 2 C3 axes, and then there's these 3 sigma planes. So let's take a look at that. That's what that says in this C3V character table. You have the identity, and then you have 2 C3 axes, one going 120 degrees and the other go 240, and then you have these C3 sigma V planes. These planes and these axes are grouped together as a class, and they all have the same character. So when you go to do these decompositions, and so on. This is the total number of symmetry operations. So if we look at here, the total number of symmetry operations 1 plus 2 plus 3, so they're a total of 6. So that means that you have to divide these things by 6. All right, another thing about the C3V is this funny E here. So we talked about the A and B, but what is the E? And in fact, here's a character that's not equal to 1 or minus 1. It's equal to 2. And over here we have a character equals 0. So what's with that? Well, let's think about that a little while. So for C2V symmetry, remember we had, say, the X and the Y, and we were rotating about the Z-axis, which comes towards you. And we started with a point here, X, Y, and Z. And various symmetry operations, we can put it in these three various quadrants here. That would be X minus Y, this would be minus X minus Y, this would be minus XY. So we can go either one of those quadrants. But what we're saying is that, oh, all you're doing is changing the sign of X, Y, or Z. This would be X minus Y, Z. This would be minus X minus Y and Z. And this would be, let's see, would be minus X, Y, and Z. All right. So we just go at each one of those four quadrants for C2V symmetry with those symmetry operations. For C3V, on the other hand, let's draw that. All right, let's put it up here into X, Y, and Z. We're going to rotate this 120 degrees. So that'd be put it down here. Now this is, say, X prime, Y prime, and Z. Z doesn't change. This is X, Y, Z's coming out at you, so think of that going around the circle. But the X and Y change. And in fact, if you try to do for a C3, represent that as a matrix, you'll have something here, you have something here, and you have a 0. You have something here, and a 0, and something, and then you have a 0 here. Let me just write that as a 0 here, and a 1 here. So what this means is, well, I just ran out of room. So let me write that down here. X, Y, and Z. This means that if you look at the transform coordinates, X prime, Y prime, and Z, X, if you multiply that times that X and that times that Y, so this transform coordinate here will have a combination of X and Y. Similarly, Y prime will be a combination of X and Y. So X prime is X and Y prime. So you need a two-dimensional matrix to describe a C3 rotation where you go 120 degrees. So this would be 120 degrees. Rotate there. Okay, and in general, for a rotation matrix, where you rotate about Z-axis, you can look this up in Wikipedia or something, you'll have this as the rotation matrix. You have cosine of theta minus sine of theta and 0. Here you have sine of theta, cosine of theta and 0, and here you have 0, 0, 1. So there's the rotation matrix. Note that when theta is 0, that is to say what you've done is not done anything, just kept it where it is. These terms will all be 1, so it'll be 1, 1, 1. And these terms, sine of 0 is 0, so these will be 0. So you have just the identity matrix, which is the identity symmetry operation. But in general, if you're rotating through something that it's not 90 degrees or 180 or something, then what you end up with is you need this mixing. You need these two things is no longer diagonal. So the irreducible representation, in contrast to the C2V symmetry, for C3V symmetry, you need a 2 by 2 matrix. And that's called the dimension of the particular thing. And what you're doing is this is called a character table, and characters are the trace of a matrix, and the trace of a matrix is just the sum along the diagonal. So the reason you get 2 here for the identity is that for the identity you need a 2 by 2 matrix, 1, 1, 0, 0. All right, the trace, or the trace, which is called the character of the matrix, is the sum of the diagonal elements of the matrix, and that's equal to 2. So that's because you have a C3 rotation. You can't just represent that by just changing one of the signs of X, Y, or Z. You have to combine X and Y, so that's 2. And then you could work out for various group theoretical methods, which I won't go into, but you can probably find that in a more advanced physical chemistry text, or of course online in Wikipedia. You'll find that the characters for this are -1 and 0. So note in the C3V symmetry you have 1, 2, 3 classes of symmetry operations, even though you have a total of 6 total, and therefore you have 3 irreducible representations. The number of classes in a symmetry group, point group, is equal to the number of irreducible representations in that group. All right, so let's see, we covered everything. Let's go back here. Yeah, so we know something about now the order of a group, the dimension of a representation of symmetry. So I think we've covered everything in this slide. All right, a little longer than I expected, but there it is.